I'd like to give you some help with the project of designing a steam power plant. To begin with, we can go to the Project 1 site. If you click on Course Materials and then find Project 1 listed. And there's the description here, which you can pull up, that gives some explanation about the project and also a little example, the details of limitations of the project, pressure, maximum temperature, minimum pressure, minimum quality that's allowed, and also a grading sheet that shows you points I'm specifically looking for. I would strongly suggest that you use these items in the grading report as actually headings in your report so that I can find them, so that you have a section called. Also make sure that you pay attention to the items that are in the appendix, and then finally that you send me an electronic copy of your Excel program so that I can look through it and see if there's errors or what errors were made. All right, and don't forget the due date, and it's 10 points per day if late. All right, let's next go to downloading the spreadsheet itself. The other link here is the spreadsheet. What you'll want to do is not open it directly because of security issues. You need to save it and then open it from your downloads. I have two copies here. I'll open the one I downloaded already. It's already open actually. So if you don't download it, you may have security problems. If it tells you that it's got security enabled, you can go to options and the trust center settings, and as long as it's something you trust, you can go to macro settings and change the settings there to allow macros to run. This spreadsheet does have macros. If you do that, you might want to re-enable or disable macros so that when you open other files you don't get into trouble. Alright, so if things are working and the macros are running, you'll see that when you enter values on this first page, so if I change this to 700 and press enter, you'll see these values will change. And if we go to, let's say, and properties are expected in kPa, so at 8 MPa, 700 degrees, we can go to find the booklet. So if we go to the superheat tables at 8 MPa, 700 degrees, we see that the enthalpy is 3882.4. And if we go back to our we'll see it's 3882, I guess 0.0, since it's not giving us so there'll be slight differences in some of the values, but these are fairly accurate. So I want you to use all the values in your calculation from the program, but I also want you to verify the final solution and your first solution with hand calculations that come from the tables, just to make sure that you did everything right. But you will see some slight variations. Here we have 7.28 for the entropy, and if I go back to the entropy at 700, 7.2812. So sometimes in the last digit you'll see a slight variation, and that's partly because there's different correlations, sometimes even different offsets for the enthalpy, but they're very close to the ones in the table. All right, let's get started with a simple model. Go back here to the spreadsheet. So there's an example here that has two turbines with reheat, condenser, pump, and steam generator, and I've got some properties that I've selected for starting. And so 480 degrees, this is also the example that's on the assignment sheet. And so on that assignment sheet, I chose some different pressures for P2. Pressure 2 is this pressure where the reheat occurs, the exit pressure of turbine 1 and the inlet pressure for turbine 2. And then I tried several different pressures to see the impact on efficiency. So you'll see here that at this intermediate pressure of 1380 is where I got a maximum efficiency of 0.3526, and my efficiency is recorded up here. So once I calculated all the properties using this program, then I calculated the turbine power based on those properties for state 1 to 2, and then multiplied it times my mass flow rate, and then adjusted for units to have in megawatts, and then I summed up all the turbine power, subtracted the work from the pump, or power from the pump, and then divided by the heat transfer in, which would be Q1, which is the original heating, superheating, and then the reheat. So those two things added together. And since 100% goes through, it's 100% of that enthalpy change times the mass flow rate in this case. And then finally, my efficiency is those ratio of those items. Okay, so that's how to set up a program. I also have a TS diagram here that changes as you change properties. So you'll notice if I change this to 4000 kPa, you'll see this line will shift on the schematic, or on the TS diagram, and that's because I've repeated entropy values for every point on the diagram and temperature values. Now I have a strange thing here that I haven't seen before, that my my entropy actually decreased there, so something, I changed the wrong value, so let me undo that. You can do that. So here I wanted to make sure I changed this one because this one is actually linked to this one, so you need to be careful when you change values. You might want to, when you have a cell on the left that's actually linking to a value somewhere else on the table, you might want to lock those cells. Or the other thing you can do is cells that are free to change, you could highlight those. Of course, we could change the efficiency if we want. Then this is the first occurrence of, well, I can change the reheat temperature. This is the low pressure. Can change that. And then other places where I'm using that same pressure, of course I don't want to change that. I can change this efficiency if I want it to be separate from that one, or I could link that together. I think I'm going to link them. So then I won't have that as an independent variable. And now everything else that's on the spreadsheet I can't change because they're tied to some of these other inputs. So these are all the possible variables that I could change. I decided to focus on this one. I'm going to put that as green for right now. So that's the one I'm working on. And then over here in this table, make that green also. Oh, that's actually an overlay there. So do it here. Okay, so here are my efficiencies for this variable that I'm working on changing. And so as I try different values, like now that I've gone to 4000, now it looks correct. Let's change it to 2000. And you'll see the TS diagram is changing. And here at 2000, I get 0.3519. So what I did is I put some values that I want to consider for that variable. And then I record the efficiencies here. So if I didn't have a value already for 2000, I would then copy this after I've set that to 2000 and just paste a value so that now I have that recorded. And then over here, I have a plot of all my values for P2 and the efficiency as a function of P2. And I see that there seems to be a peak here around 1380. And so I've optimized the operation of this power plant to its maximum efficiency given these other conditions, so which is at 1380. Then I might want to start looking at, well, I wonder what would happen if I increase the temperature. So now that I've optimized this, I will leave that. So I'm going to now fix that, and probably should note that somehow. And I need to write down the order. So that's one of my fixed variables now that I've set. And now I can take this as my first iteration of optimization. And I probably should also record what the other values were. Maybe I'll take this whole thing, just so in my first iteration of optimization. And so based on these values, just put a box around it. And I'll probably arrange this better later, but for now, these values right here correspond to just drag this over to the inputs below, so I can then recreate those if I need to and don't lose track of how I came up with these efficiencies. And then now I want to create a new variable, so I'm going to use T1, and in C, it's probably going to change it to copyright, so don't want it to do that. T1, I think if I do that in 2 steps, it won't do that. Okay. So I'll start with maybe 480 is probably about as low as I want to go. Let's try 450, 500, 550, 600, 650, and actually I wanted to have 8 values, so I'll try a few in here. 625, 650, 675, and 700. Now I have some suspicion of what's going to happen here, because I know that as my high side temperature gets, my maximum temperature gets higher, the Carnot efficiency goes up. So I would assume a similar thing would happen for the Rankine cycle. So the higher my fuel temperature, the more efficient that my production of or fraction that's converted to power will be. Also, the lower I make the condenser temperature, the higher efficiency I'll have. So as I lower the condenser pressure, that will probably also increase the efficiency. So I'm going to try this next. I'm going to make this one green, so I know what I'm working on here. And so now I have to calculate new values. Of course, I can also record the total power, which should just be the sum. I wanted to add another line here, and that's going to equal the numerator of my efficiency. So the sum of those two minus the pump work or power, and I can also copy those here. Alright, so we'll start at 450, and I get an efficiency of 0.3486, and then continue on through, try 500, and I guess while I'm doing that I should also put my power in here. Go back to 450, get my power. Okay, I'm going to do the rest of the values. Make this, don't need quite so many digits. Continue this, which will finish plotting the graph, but I'll pause this while I do that. And finally, I'll enter 700. And I moved my power over here since it was easy to copy both of these together. And so now I've finished. I'll clean things up a little bit, change my number of digits to a reasonable number, and I'm going to leave this here for right now. I know what it is, but I will probably remove it since it's hard to label there. So now I have all these values, so I'm going to grab this, paste that for the next step of my iteration. I'll paste values again, and this time copy this, my results. Okay, so now just to recap, I've got I'm not sure why this, so I copied slightly different values, so let me So I know what my settings were in this case. So 1380 was the thing I was varying first, P2, and now I'm holding that constant and varying the temperature, T1, and these are my results. So I can clean this up a little bit. And then I notice here, originally my axis was set, so I probably want to use the horizontal axis to auto. And I guess I can still have it go to 0. So what I'm seeing here is that the temperature just continues to increase as I adjust the temperature up, which probably makes sense in that my efficiency, I would expect it to go up the higher the temperature difference between my low temperature sink and my high temperature reservoir. Now what's a bit strange here is I almost have no reheat at this point because I've raised that temperature so high. So the next thing I'm probably going to check is if I could increase this. Let me turn this to red and give myself a little more reheat here. So I'm going to do that, make that green now. This will be my third parameter, and I probably don't want to go less than that because then I'd actually be cooling it rather than heating it, and that of course won't help efficiency. So my third parameter that I'm going to vary is T3, and I'll start out again. I'll start with 450, I guess. Delete these values, and I probably actually should have changed the label on there, but I'll leave that for now. And when I finally print out my final graphs, I can change the label on my plot. So I'll start at 450, and I'm holding it at 700 at 1380, but now I'm going to vary this, and I'll copy these values, paste them here as values, go looks like I can do the same variation so that I did for the other. So 500, and then of course this isn't pressure 2 really, this is temperature 3. So if you wanted, you could make new plots for each, but for now stretch this out a bit. Had to shorten this to get my title not to go over the graph. So I got up to 600 degrees, and I notice now that at the exit of my turbine 2, I'm starting to come out superheated, which may or may not be desirable. I'm seeing though that the efficiency seems to be rising as I'm allowing the reheat to go to higher and higher temperatures. So I'm going to continue on with that and kind of keep an eye on what's happening here at the bottom. Okay, so I went all the way up to 700 degrees, recorded my efficiencies. Now I have a new table with power and efficiency for optimizing that variable. And I see again that my efficiency continues to climb. I have quite a bit of superheat coming out of turbine 1, but it is at low pressure. So I don't have any problems of tearing up my turbines. It's superheated throughout both turbines. And I can now record this as my final parameter that I've optimized. Let's grab this again. Paste that here. And then same thing, get the original values. And paste those. And also, I guess I grab the headings there. Okay, so now I have documentation of how I did this process, and so my first iteration was to vary P2, optimize that to 1380. Then I held that value. The next step was to vary T1, get the maximum efficiency. So each time my efficiency is going up, and then the final time holding those two values is to vary T3, and it looks like that was also at 700. So my original efficiency that I started with, I think was, I forget what pressure I had in there originally, but somewhere around 30.34%, and now after some optimization I'm up to almost 40%. And so if this was the end of my optimization process, this is the steps that are required for your project. So you pick 3 parameters. So I've got my 3 parameters that I optimized over. I did them, actually I want that to be black. And there are still some other parameters that I could have adjusted. Of course, I could have run this up to higher pressure. I could have played with efficiency. Of course, the higher the efficiency of the turbine, the more it's going to cost. Maybe I could have gone to a lower condenser pressure, but that's pretty low. All those things would also affect efficiency. But you can stop at 3, and at least it illustrates the process. Now, just for curiosity, I'm not going to save this for part of my report, but if I go back now and adjust this pressure, so maybe even though I optimized this, let's see what happens when I go to 1500. So here my efficiency was 39.89, and goes down a little bit at 39.83. And let's try a little bit lower. Let's try 1200. And 39.99. So we actually went up slightly, not much, but from 39.89 to 39.99. So there seems to be a little variation in that the new optimal mid pressure has changed a little bit. And if we go in one direction a little higher, see if that goes up or down. It's still going down, so we might consider, say, 1150. And now it's 40, 1100, and 40.4 thousand, and it's climbing, but not nearly as much. continues to climb, but not affecting efficiency a tremendous amount. But so we might find that after we've adjusted these other parameters that we get a new optimum, and then we might have to go back after we change that and revisit the others, and you could go back and forth. For this project, since you're not working on the design for a year, just do 3 parameters. You can pick them in an order, but once you optimize one, hold that fixed, leave that constant. As you vary the next parameter, hold that fixed, and then vary the final parameter. If you want to play around a little bit before you start and look for a fairly good efficiency, you can do that, but it's nice to show just from a random selection of properties how it increased significantly as you do a quick optimization. Right, I hope that helps. In the next tutorial, I'm going to just show you about building the model yourself and how to construct this table here. Of course, we're just using with my design, and I think I'm going to restrict you from using this design for one of your 3 designs, just because we have this one already. But you can use this to kind of get an idea, a feel for how the power plant works, also for what things might increase efficiency. Of course, we know that the higher the fuel temperature, the maximum temperature in the plant, that will tend to raise the efficiency. The lower the condenser pressure or temperature associated with that, the higher the efficiency in general will be. And then if all the heating can happen close to this high temperature, then that will raise the efficiency. So if somehow we could have, maybe done this heating with some of the reject heat, which is called regeneration, we'll probably also see an increase in efficiency, because we have this huge 600-degree temperature difference here in the boiler, which heating through a big temperature difference like that is always going to reduce the efficiency. So those are some ideas. Try and understand them, explain them in your report, so that whoever's reading the report understands that you've got some methodology of why you're doing what you're doing, rather than just its trial and error. All right, I'll show more about the particulars of setting this up in the next video.